Good afternoon, and welcome to the fourth CERFA webinar. Our title of today is From the Local Universe to the Most Distant Galaxies. I hope you will enjoy it. So the speakers of our first Astro webinar are Eduardo Ros, Miguel Requena, Fernando Buitrago, and myself, Rebecca Garcia. So, oops. See if I can pause this. Okay, now. Okay, so the first speaker will be Eduardo Ros, and he's going to talk about observing black holes. And he is the scientific coordinator of the Department for the Very Long Baseline Interferometry, and he's also an associate professor for astrophysics and a member of the Astronomical Observatory. The next speaker will be Miguel Requena Torres. He's a postdoc at the Max Planck Institute for Radio Astronomy, and his talk is going to be SOFIA, the stratospheric observatory. Then is going to talk Fernando Buitrago. He is a postdoctoral researcher in at the Edinburgh Observatory, and he's going to talk about the most massive galaxies. And the last one is going to be me, and I'm also a postdoc at the Department for Infrared Astronomy at the Max Planck Institute for Radio Astronomy, and I'm going to talk about the formation of the stars. So after each of these talks, you can make questions. You just have to raise the hand. You will see there an icon with a hand. You just click in there, and then we will answer all of your questions. So let's start with Eduardo. Eduardo, you have it.
Okay, I think you can hear me. Then let's go to the content of the first block of the webinar. Yeah, just well, the topic today is to observe black holes at the edge. At the edge, you will ask yourself, what do I mean by the edge? That means at the edge of what is really possible, because one of the characteristics of the black holes is that they are assumed to be black, or at least not to have much color, maybe to have some hairs or so. If we classify the black holes, the first classification we can make is about the ability to rotate or not. At the left-hand side of the transparencies of the slides, we can see what is called the Schwarzschild black hole, which is not rotating, and the main characteristic defining it is the event horizon. Anything going beyond this horizon cannot live anymore because its escape speed would be higher than the speed of light, and then remains there forever. At the right-hand side, you can see the Kerr black hole, which is a rotating black hole in the most extreme case. There you can see not only the event horizon, but also the ergosphere, which is a kind of event horizon as well, which is caused by the frame dragging of the space-time by the rotating black hole. Actually, we cannot see there. We can only deduce that there are black holes by different characteristics we can observe in celestial bodies. We can see that they are doing something to their environment. This environment is full of matter which is falling into the black hole. And we can see, for example, in active galactic nuclei, which are galaxies that emit light across the spectrum with a very high brightness, we can see, usually with our radio telescopes, for instance, we can see two big jets that are emanating from the central region of these galaxies. If we observe that also with X-ray telescopes, for example, we can see that something is happening very close to its center, and by the study of their spectral lines, we can see that there are relativistic speeds. That means speeds going close to the speed of light happening in their central region. These black holes are assumed, or we can weigh them, we can know how heavy they are, and they can reach even masses of billions of solar masses. This can be deduced as I mentioned, by independent methods. If we want to observe them, we need some powerful instrument that is able to distinguish the details. If we would use our eye, we have two detectors in the face, sometimes with a lens. We have glasses, which are tuned at the frequencies of wavelengths of about 5,000 angstroms, so we see the top. Then our eye, naked eye, has a resolution of 1 arcsecond, as you see in the left. If we compare that with a big radio telescope of 100-meter diameter, this is exactly the same resolution it can reach. If you want to get better resolutions, you need to either to change the observing wavelength of your instrument, or you need to increase the maximum size of your telescope. There's a trick to do that, which is called interferometry, and with that you can use an interferometer with thousands of kilometers of size, of baseline, we call, and that you can reach resolutions which are 50 times better than even the Hubble Space Telescope. You go up to the milli-arcsecond resolution, and in the bottom panel you can see how you would see Jupiter with your eye in the left-hand side up to the resolution provided in Io, one of the satellites of Jupiter, with a telescope that would have the resolution of an interferometer. We can enhance this by using what is called very long baseline interferometry. You put radio telescopes at the edges of the Earth, and if you want to make things better, you can pull a lot of telescopes, and if you even manage to arrange an instrument with a square kilometer in collecting surface, we are looking into the square kilometer array, which is a project for the 2020s, 2030s, which is starting now to take speed. This is one of the big astronomical projects, together, for example, with the extremely large telescope or another things like CTA in the Cherenkov wavelengths. Or if we want to enhance our telescope, we can tune in the equation of the resolution the lambda. We can reduce the wavelength and go to millimeter wavelengths, which are the extreme case you can observe in radio astronomy without being very affected by the atmosphere, or you can tune the baseline. And the most extreme case is that since the Earth is not enough, you can go to external space and try to get a radio telescope in orbit and do interferometry with that. We can see that in a cartoon. Here, for example, we see, not to scale, of course, how would work an interferometer based on the Earth with very long baseline interferometry with several dishes here and there. And if you, also not in scale, put a telescope in orbit, you can synthesize a telescope as big as the Earth. You have as big as the Earth or as the diameter of this orbit. This is happening at present, for example, with the Radio Astron project. It's a Russian telescope that can reach even the distance of the Earth to the Moon and can beat any record in resolution in astronomy for many years, I guess. But the interesting thing is, for us, if we want to go close to the black hole, to the center of one of these galaxies, we can tune, as I mentioned, the wavelength. And you see here in this panel, you can use a connected interferometer like the VLA at the top side. Then you see a nice radio galaxy with two lobes. If you zoom into that with VLBI and go to higher frequencies, you can access to the heart of these active galaxies or of these bodies. If we look into the closest black hole that we have to us, this is the huge black hole at the galactic center, which is assumed to be 3 to 4 million of solar masses. And here you can see a picture taken in the infrared of the stars around the region of the galactic center. If you see these spots which are moving around, you can deduce their speeds, you can apply Kepler's law, and you can deduce the mass of a body which is there and around which all these stars are rotating. There, if we observe that with radio telescopes, we see a very bright spot. This is our galactic center, and we know that there has to be a black hole there. And in the next years, the idea is to try to tune our telescopes to observe its vicinity. Now imagine you would like to see a black hole. You don't see actually anything because, as I was telling, the light is falling into the black hole itself, but you can deduce the mass and the environment of the black hole by looking around it. The parts of the black hole behind it, if you, now that the black hole has a disk around it, get carved, and at the end you see an image like that, like a kind of donut or ovni, UFO, whatever you want to see there. This is what we expect to see as a black hole. And actually what we want to see is what we call the shadow of the black hole. If we manage to do that over the next years, we expect to get that next year, then we can do things like testing, as one likes to say, if Einstein was right. We can test there the general relativity. We can see also, for example, if the black hole is rotating in the same direction as the galaxy, that would be the smallest shadow, as you see in the left-hand side. If the black hole is not rotating at all, or if the black hole is rotating in the opposite direction, then you would see this kind of hole, and there is deduced also what is the innermost stable circular orbit of matter falling into this black hole. To do that, we need to go to very high frequencies, and we need to go to the southern hemisphere. If we now sit at the galactic center and look into the Earth, the galactic center is quite far to the south, and to get an array which is able to observe millimeter wavelengths and see properly the black hole really high in the sky, you need to go there to telescopes like the South Pole Telescope, to the Large Millimeter Telescope, which is being constructed in Mexico, in Hawaii, or in Eastern California. If you want to do that, including telescopes in Europe, you have the two telescopes of IRAM in France and in southern Spain. But the best of all, which is now under construction, well, it's just finished, it's starting observations, is the ALMA telescope in Chile, which you see there. And this one would be extremely sensitive, extremely powerful, and gives you very nice baselines, intermediate baselines, to be able to get a very nice image of the galactic center. To do that, there is a caveat. This telescope is made of 50 dishes, which are separated over the desert in Atacama at 5,000 meter height, in one of the best places of the Earth to observe without disturbances of clouds or any other troubles. But you need to make all these dishes, all these telescopes, to work as a single one. To do that, you need to do something which is actually happening every time in your pocket with your mobile phone, and I explain you what is that. Here in this picture, you have the different antennas at the center, and if you get the waves from any celestial body and you introduce a delay between them, you can synthesize a single antenna which is observing in the direction of this, what we call the beam. And by tuning these delays, you can tune the direction of what you are observing. Actually, that's happening with 4 mini telescopes. They are actually mini antennas, which are distributed in panels at the top of some buildings, and they look into your mobile phone in your pocket or in your bag, and by looking into that, facing its signal, are able to connect with you without losses. If we manage to get ALMA phased, we will be able then to see the image of a black hole as you see in this panel. In the central panel, you see what are the phases of your observation. This is a measurement of the quality in the interferometry, or, I mean, one of the quantities you can measure. You would see a lot of noise in your detections, but if you add ALMA, you have the right-hand side image, and then you can really distinguish in your model if you are looking into a donut or into a half moon or just into a disk. And this is the way you can detect the black hole, and we expect to do that in the next year. For that, there is a huge project now working with several tens of people and dealing with ALMA to make it compatible with these observations. And this is a very complex process, which is just shown in this plot. I will not go to enter into the details, But this is now the challenge to make ALMA during the second half of 2014 and the first half of 2015 able to observe all together to be able to see this telescope. And just to support that, the European Research Council recently granted a synergy project, just a couple of euro, 40 million euro were dedicated also to support this project, which is done in collaboration with the US, and several countries in Europe, and also Taiwan, Japan, Korea. This is the so-called black hole camera, which is coming very soon. Then, if everything works, if we manage to face ALMA, the software has been tested, by performing very long baseline interferometry, we will be able, hopefully next year, to get the shadow of the black hole in the center of our own galaxy, and also we will be able to discern if Albert Einstein was right, or all his general relativity theory maybe has some flaws, or we have to adapt it. And this is one of the observational challenges in astronomy for the, I wouldn't say for the next year, just for the next months. We are very close to get that. Okay, and this is what I wanted to tell you. Thank you. If you have any questions, I'm ready to listen to them.
So, any questions? Okay.
I don't see the
So,
chat.
you have one question. I think we can hear you.
Yeah, where?
Oh, no, Jean Jacques was raising his hand. No?
No question?
Give me a second.
No, since everything was clear.
Yeah.
Or obscure, like the black hole itself.
We just gave access to Jean Jacques. So it looks he has a question. Okay, so if there are no questions, we will continue. Thank you very much, Eduardo.
Sure.
And the next speaker is Miguel Ángel Requena Torres. Oops. Miguel, you can start.
Well, yeah, now it's working. Sorry.
Okay.
You hear me, right?
Yes.
First of all, thanks for coming and seeing these talks. And I will present something not directly related with my science, but with the telescope I'm using. I'm member of the great instrument team on board of this nice plane that you see in the picture. That is SOFIA. And just to be you will be able to see me here in the picture in front of the observatory. And now to give you a small introduction on what is an observatory for us, I will show you first what would we do see, the astronomers. We receive light from all the universe, but this is a really long range of possible ways to see this light, this emission from the universe. What you see here is just our own galaxy. As you can see, the electromagnetic spectra that is emitted by the material is really long. I mean, you see X-rays and gamma rays with the electromagnetic spectra being really short wavelengths, like the one that Eduardo was saying, and the wavelength of these spectra is changing as the way that we move into different ways to see the light. The optical light that we see with our eyes is this panel here, and then we have the near infrared or the infrared emission that we can see in different ways in our galaxy, and then we have the longest wavelengths that are the radio continuum that Eduardo was observing with his PLBI and other telescope. All these spectra, the SOFIA observatory does from the optical to the infrared observations. And why this? What we have so many telescopes looking at this, because every different range of the electromagnetic spectra is different in the way that we can receive the emission. In the radio wavelengths are really weak, and the X-rays and gamma rays is really strong, but it's difficult to see. One of the problems is our own atmosphere. Here I plot a series of telescopes for several signs, like radio antennas, like the one of GBT in United States, or satellites, as you see. And the point is that this emission from the universe arrived to us only to the ground-based telescope in the optical window. Only the visible light and part of the ultraviolet and infrared light we can see, and also the radio window. But the rest is blocked by the atmosphere. It's just absorbed by the atmosphere, and it doesn't arrive to us. Then we have to go to satellites for some of the areas, and then if we use stratospheric observatories like the planes, we can go high enough to go above the atmosphere that is blocking this light. This is what we have with the stratospheric observatories. The first one of that, well, before I wanted to show also from Eduardo, VLBI is a combination of several antennas. So this is another way that we use observatories, of course. Then one of the first stratospheric observatories should be like the balloons. There were projects since 1957 where you put an instrument in a balloon and then you leave it go, and then it goes in the atmosphere for a while, and then it goes down a bit. One of the best places to do these observations is in the South Pole, because there the currents of the winds make the balloon just go in circles, and it can have circles during 48 days that cover several times the South Pole, and it goes high enough, 39 kilometers, to about this part of the atmosphere that is blocking the infrared window, for example. But NASA was one of the first that used planes to start avoiding the lower part of the atmosphere. In the 60s, they just already use a jet, a normal jet, like the private jets that you see nowadays, but they make a hole in the top, and then they put one single instrument, a photometer, that was observing the sky. It was a 30-centimeter mirror that was looking up the sky. Then in the 70s, they update this way to think about the observatories, and then they create the Kuiper Airborne Observatory, KAO. And it was a bigger plane, a Lockheed C-141A, with a bigger mirror. It was a 91-centimeter telescope on board this. It was quite packed inside, as you see in the pictures, that the people were just really in a narrow space up there. And the good thing is that the mission covered 20 years, and they could be able to change the instrumentation, to update the instrumentation, and they were flying high enough to avoid all the infrared atmospheric absorption. And this mission was ended in 1995, and in 1996, the SOFIA project started. A combination of a partnership between the NASA and DLR, that is the space science organization in Germany, was established, and then there was a partnership of 80% for NASA and 20% for DLR. They create their own institutions to take this mission, And then the United States, the NASA bought a United plane, a 747, a special plane that they then become NASA. And then the Germans, what they did is make the telescope. They did the dish, they did it in Germany, and then they put all together in Texas, in I think around the end of the 90s. And then we got SOFIA, that is a 2.5-meter telescope inside this Boeing 747 Special. You see in the back here how the door open and you can see the mirror. The point of this telescope is that you can move all around the world. Now it's a bit limited for the moment, but at that point we can go anywhere. And you can change the instrumentation. In normal telescopes, you can change it every few years, and in satellites, you can never change it because they are so high that you can not reach it easily. But then we have this in California, where the NASA Dryden is in Palmdale, in north of Los Angeles, and the scientific center is in San Francisco. The idea is to have 1,000 hours per year, and in a 20-year lifetime of the plane. It's the world's largest portable telescope, and is supposed to go to the southern hemisphere at least one per year. Just to give you an idea of how it moves the antenna, this is a sketch of the antenna, and this middle section is the connection between what one sees inside the plane and the cavity where the mirror is. And then this it moves completely isolated from the plane because it's like a semi-sphere floating in an oil layer that is at the right temperature to have no friction at all. And then when you have turbulence in the plane, what you see is the instrument just moving like crazy, but what is moving is yourself, of course. Here is a sketch of the plane itself, where you have the cavity with the telescope in the back, the instrumentation looking to the observers, and then you have a big space in case you need to put any other instrumentation. You have the observer racks, the operators of the telescope rack, the mission director, and then you have a space for educators, for teachers of high school, that they are allowed to go to the plane to then follow the observations and then teach to the students. Germans and Americans professors have been there already, and then this in the high part of the plane will be the pilots and engineers from the plane. Here you put the instruments, and there are right now 7 instruments to be there. Just before showing you the instruments, I wanted to show you the flight that we have in between 2010 and 2011, that it was the first time that the SOFIA was flying. We have mainly in the mainland United States and in the Pacific. There's one trip to Europe to make an air show in Germany. And then in the 2013, we did the southern deployment, where we observed several sources in the southern hemisphere, and then we stay in New Zealand. And now I will show you the instrumentation that we're using. What we try to observe here is several things, to see from solar system planets to star-forming regions, from the initial part of the star-forming regions to yes, when you have a stellar system, or where you have supernovas. I mean, everything that you can observe from the submillimeter regime of wavelengths to the optical. And one of the things that we do is also observe molecules. This is a resume of the instrument. We have HIPPO, FlyCam, Forecast, and GREAT that has been already in the plane. And the new instrument that arrived this year are XS, FIFI-LS, and HAWK. And I will just give you a bit of information about each one. And we'll be there. Forecast was the first instrument in the plane. You can see here how is the back of the telescope, and here is the instrument that is attached here. Here you have part of the instrumentation as well, connected to the instrument. And this is like a CCD camera, but for the infrared. You have 2 colors, and you can observe 2 things at the same time with a small camera like this. This is the element of observation. And you have a really good 0.75 per second resolution. That is nothing compared with what Eduardo was saying before, that it was really small sizes, but it's good enough for these wavelengths. This is the cover 5 to 35 microns. And what they did in the first years is observe solar system object like Jupiter, and they did observation of the atmosphere, where they studied the temperatures of the atmosphere. And they can go to the galactic center. This blob here in the center is exactly what Eduardo was telling before, is the place where the black hole is located. But what we see is an area that is quite far away. And then we see how the material is getting in. What they see is dust, is small particles of dust that is in the interstellar medium. And this is our galactic center, and this is a galactic center in another galaxy, M82, that recently they had the supernova, and then there were a lot of observations about it. Next instrument will be great, our German receiver. That is a heterodyne spectrometer. What we don't see images, we see just spectra, like I show in the bottom. That is every molecule that you have in the interstellar medium that is molecular clouds of material that then compress to form stars, for example. Every molecule have a special fingerprint in this electromagnetic spectra that is like emission lines or absorption lines that you can get with this instrument, for example. What we did in the first years, I wanted to put a few of the science highlights, is the detection of new molecules that were not discovered in this frequency range, like SH, sulfur-bearing molecules, or deuterated barium molecules that are really weak because the deuterium is really not abundant in the galaxy. Then you see really nice absorption lines where they were expected to be, but they were really weak, and we spent really a lot of time then. I wanted to show my own project that is in the galactic center as well, but as I said, it's really far away from what Eduardo was saying. There is a molecular ring around this area that is the material that is still in molecular form. When you get inside this area, all the material is ionized, the molecules are destroyed, and then you can only see stars and very small condensations of things. And I did the estimation, the analysis of the excitation in this area. And what we do is we have only one element of resolution, this spectra in one point, but we did a lot of maps as well to study the molecules in areas. But this was poor and inefficient, and now we will get a new receiver within Gray that is upgrade, that will be a 19 element receiver. It was a 7-pixel in one band, 7 pixels in another, and 7 pixels to get another polarization in the same place. Then we will have a very big machine for doing maps. Other instruments that have not so much time, and I will just put a few things, is HIPPO, that is a high-speed imaging photometer for doing occultations. Okay, it's like a CCD, but really fast, that you can get a lot of information directly. And then the main thing that they did in 2011, it was the occultation of Pluto. You have a star here that you cannot see, but there was exactly the time that the Pluto was passing through, and this is the way of the eclipse where the eclipse was going on, and then this is the flight plan of SOFIA. Then in this point, they did the observation. They were looking when exactly the Pluto was passing through, and then you can see the spectra of the star, and then how Pluto passed, and then you can see the first part of the atmosphere of Pluto itself, and the other part of the atmosphere. Then looking with several wavelengths, you can do estimation of the atmosphere and of the surface of Pluto, what they did in a paper. Another instrument that just finished the commissioning, that is the studies of the instrument in the telescope to see if it's working properly, is FlyCam, that is an infrared imager that can do a spectra as well to observe really big molecules, the PAHs, that are just combination of several carbon chains molecules. And then you can see images of it like this in the Orion Nebula. This HIPPO and FlyCam actually can work together if you put HIPPO in the bottom and FlyCam in the top, and then you have a nice optical and infrared observatory instrument. It's FLIPO. And then you have 3 instruments that we have never seen in the telescope yet, and it's XS that will give us extensive spectroscopic and imaging possibilities for the 4.5 to 28 microns regime. And Hawk, that is something special because this electromagnetic spectra, when it's found some part of some different physics like magnetic fields, it gets polarized. You can actually see this in this sketch, that you see how this wavelength that is like a wave in space, it can be in some kind of direction. It's a vector, and it can be rotated. Then depending of what you see in front of it, of the emission of this light, it can change. And then this polarization can be measured with this Hawk plus, and it will give us an idea of, for example, the magnetic fields in the area. And the last one is FIFI-LS, that is again an spectrometer, but with 5x5 elements of resolution. Then you will have maps and spectra at the same time in the same wavelength that we have in great, but with a better, much more sensitive, but less resolve in frequencies. And this is also the other instrument from Germany. The other ones were all Americans except great and FIFI-LS. And that's it. I wanted to say, just give you an overview of the observatory. That is one of the more extreme observatories because it's just in a plane and we fly 3 days per week. It's a very different instrument covering a large wavelength, and they can change, and they are changing already. Then there will be a 20-year missions with a lot of nice things to see. Thank you. This is what I wanted to say.
Thank you very much, Miguel. So now the turn for questions. Any question? Don't be shy. Okay, no questions. So we will continue with our next speaker, that is Fernando Buitrago.
Hello? Yes, now you could hear me. So I was telling that first of starting with my presentation, it would be nice if the organizers could tell us about how exactly to raise these questions, because for those of us that are new in this program, it is not obvious where we need to click in order to raise our questions. Well, as I see
so,
that the organizers
you have
perfect.
Okay, no, yeah, I'm there. So you have apparently, because my panel is different, you have a hand where you can click on it. It's on the left side, I think, of the panel. Can you see it?
No.
No?
No.
And then if not, you can also use the chat. There is a chat.
I tried to use the chat before, and I couldn't type.
Fernando, you can ask questions because you are a panelist. It's only probably will be only be available for the attendees. This hand is a yellow hand that it should be anywhere in the menu, but it's a clear hand. Yeah.
So
anyway,
it is not for us.
No, because you have the voice now, and at any rate, there's a question section and a chat question where everybody can ask questions anyway, and I will receive them all.
Okay.
So I don't know why I couldn't type on my computer. It was only that.
Okay. Okay.
Well, during the roundtable, we can discuss it as well. Try during the last session to ask me the question, and I will forward it.
Perfectly fine. In that case, I will start with my presentation.
Okay.
So, yes, full screen right now. I hope that you can see it from your places. First of all, thank you very much to the organizers and to the CERU and CERFA for the opportunity of presenting this talk that it's going to be on the most massive galaxies on the universe. And, you know, galaxies are these big conglomerates of stars that fit the entire universe, and we are going to speak now about the most extreme cases. And I hope, as this is also a Spanish research association, that many of you have picked up that what I have at the background of my presentation is the dome of the old library in the University of Salamanca. Anyway, let's not speak about our country, but speaking about science. So here in this first slide, I'm showing you one of the last pictures of the Hubble Space Telescope, which is in a galaxy cluster. A galaxy cluster is just a concentration of galaxies. So to give you a flavor, people live in the countryside or sometimes live on towns or in big cities. And a cluster of galaxies is a big city of galaxies. And in the city of galaxies, I want you to guess which one are the most massive galaxies in this picture. I suppose that many of you had the right guess, were these big blobs in the very center. However, these are not the normal galaxies we are used to see in the beautiful pictures in internet. For us, things are more like the galaxy in the middle that it's blue with spiral arms. So why on earth is going on? What are these big balls of stars? Well, one of the things that you may know is that astronomers used to classify visually galaxies into two different kinds. On the right-hand side, you have the typical spiral galaxies we are used to see in the beautiful picture, as I was telling you. So some of them are normal spirals with spiral arms and a galaxy disk, and others have bar in the center. And for example, we think that our own galaxy, the Milky Way, has a bar as well. And in the left-hand side, there are other kinds of galaxies that are called elliptical galaxies, which are balls of stars that instead of being dominated by rotation of the spirals, they are sustained by the gravitation of the random motions of the stars within the system, what the astronomers call the velocity dispersion. So you have things here that rotate, you have here that don't rotate, but move, as I told you, chaotically. And some systems in the middle will have intermediate morphologies with this, but without the spiral arms, and other lenticular galaxies, and you can find also some irregular galaxies as well. The point is the following, that we live in, if we believe that we live in a universe that is dominated by the cosmological constant and with dark matter, galaxies should form in a hierarchical way. And what is the meaning of that? Well, so in theory, everything started in the Big Bang, and the primordial fluctuation, that comes from quantum effects, every time got more and more powerful and formed the first stars and the first galaxies. And these ones form disk in the beginning of everything because of the conservation of the angular momentum. So if things are rotating, they keep rotating. And this very small primordial disk accreted more and more materials and clashed to each other, or merged, as we said astronomers, as in the pictures in the movie I have in the top of the screen. And at the end of their lives, instead of having a disky morphologies, they form these big elliptical balls of stars, big elliptical galaxies that I showed you before. So here also you have an idea of how is the large scale structure of the universe, with many filaments in which minor galaxies go to collide with things that are in the center, that are the big galaxies. I was telling you before, these big elliptical galaxies. So here we are in our local universe with our telescope trying to look as far as possible. In this universe, I was telling you that is dominated by dark energy, and also there is a substantial amount of dark matter, while normal matter, atoms, are only 5% of it. And out of them, only traces are the normal atoms we have on Earth, such as carbon or hydrogen. because most of them are, sorry, it's a carbon or nitrogen, while most of them are hydrogen, which is the material that fuels the stars. And we can see these atoms by means of spectra. So here you have a spectrum of the sun in which you can see absorption lines, which are telling us which elements are composing the sun. But if instead of our sun we look farther away, so for example in this galaxy that is 1 billion light years away, you can see that is a tiny displacement of the absorption lines to the right-hand side of the spectrum. To the red, in this right-hand side of the spectrum, is what we call that these absorption lines got redshifted. So, okay, if you are only 1 billion light years away from Earth, you get a tiny displacement. But if you want to see things that are in the primeval universe, in the very ancient epochs of the universe, you must look not in the optical wavelengths, not in the normal light, but instead you need to go to the near infrared. The problem was that until 15 years, 10 years ago, so end of the 20th century, beginning of the 21st century, we didn't have access to good near-infrared detectors. But then we reached a moment in which we finally got them. So we wanted to see galaxies in the beginning of the universe. And what we saw? Well, we had many, many surprises, especially concerning these very massive galaxies. So they were already in place in the beginning of the universe. So not in this hierarchical universe I was speaking to you. So the galaxies form because there are mergers of minor galaxies, and at the end of the history of the universe, you form the most massive galaxies. However, the striking result was that they were already in place at large cosmological distance. So this is going to be the most difficult plot I'm going to show you in this talk. I apologize for it. So this is a plot of just the numbers of the numbers of galaxies with according to their mass, and also in different distances. So this is the local universe, and this is the very old universe. And what we can see here is that the most massive galaxies are not many numerous, while normal galaxies with less massive galaxies are more numerous in the local universe. And as we progress in the history of the universe, galaxies are less common because they didn't have time to form. However, the funny thing is that by looking here at the local relation, that it's also overplotted with the gray line, these most massive galaxies of the history of the universe were there even in the very, very old history in the universe, at very high redshift. Do you remember what I told you? We don't speak about distances. We speak about redshifts because as the universe is expanding, the distances are always evolving, and we need to speak about the redshift. And you can see that in the very ancient eras of the universe, these massive galaxies were already in place. Not only that, and this is part of my thesis, these galaxies were completely different. So regardless whether they were disks or they were spheroids at that time, at the very old universe, their sizes were very, very, very small. So if we parameterize the size we divide the size by the size of the same galaxies in the local universe, we see that these galaxies have 20% or 50% of the sizes in the local universe, effectively making them 3-5 times smaller than the local universe counterparts at very, very far away distances, say at 85% of the life of the universe, because it's the same of speaking about in time or in space. So, or if we go almost close to the Big Bang, these galaxies are extremely compact, actually with densities comparable to the densest objects in the universe, in the local universe, that are the globular clusters. Not only that, if we have a look in the morphologies, and here I show you how the morphologies evolve with redshift. So you have here massive galaxies in the local universe at intermediate distances and very, very far away, so using just near-infrared information. And then looking at them, if we plot the percentage of massive galaxies versus the distance, the redshift, we see that massive galaxies were only elliptical galaxies, early type galaxies, only in the local universe, very close to us. And if we go farther away, we need, if we sum up the contribution for late type objects of disks and more irregular galaxies, they account for 80% of the massive galaxies. Also, funny thing is these galaxies, massive galaxies, in the beginning of the universe are forming stars like crazy, like 100 masses per year, so 100 suns per year. And if we go to close to our local universe, they just form 1 solar mass per year. That is the same star formation rate as our Milky Way, but being much bigger than our galaxy. Our galaxy is just, say, 10 times smaller than the galaxies we are speaking about. So comparatively, they form very few stars. So in that case, what do we think that happened with these massive galaxies? Why all these changes? Well, so we think that these galaxies were formed, as I told you, very, very close to the beginning of the universe. Say only a billion years afterwards, they were mergers of galaxies of these primeval disks I was speaking to you about that contains lots of gas. And as they contain lots of gas, when they merge, they produce huge amount of stars. So there was a lot of gas and a lot of stars in these galaxies. But as Eduardo was saying, in the center of the galaxies, there are supermassive black holes. And these massive black holes create a lot of gas and a lot of stars. And their jets and their radiation make all this to quench the star formation of this star and to form these very compact remnants we were speaking about. And these remnants start merging with other galaxies, and as time went by, in our redshift you can see 10 billion years from this part, from this epoch to this epoch, they form the big local elliptical galaxies we can see in our universe. So for example, M87, that is the closest massive galaxy we have, is the core of the Virgo cluster, the Virgo city of galaxies. However, my colleagues in Canary Islands were very interested for the idea about, according to simulations, there might be some of these massive galaxies that live quite isolated, so they couldn't go from this phase to the big elliptical phase. So we can, in theory, see in our local universe one single galaxy that it's still very compact from the high redshift universe. However, all the quests for these galaxies nowadays only found quasars or very young galaxies. Here you have all the galaxies, the size-mass relation for all the galaxies in our local universe. And no galaxy are a truly relic from the old universe. Well, not only one, that's not perfectly true. So 2 months ago, we found finally the first massive and compact galaxy in the local universe. So you can see here the galaxy, well, it has 2 galaxies close to it because it lives in a galaxy cluster, but once you remove the light contribution for all the galaxies, here you have our relic from the old universe. However, this is very odd because, as I was telling you, we hope that this galaxy will be isolated. However, it lives in a cluster. Not only that, by this photograph, it is not clear whether it is a disk of an asteroid. Actually, we know that it's rotating very, very fast, but at the same time, the chaotic velocities of the stars within the system are also very, very high. So it is not clear at all whether it's a disk or it's an elliptical galaxy. And we are conducting many, many proofs nowadays to try to know more about this massive and compact galaxy, because we hope this is going to be a window to the faraway universe. So I really hope, guys, that during my time I convince you that these massive galaxies are very interesting to try to understand our current paradigms of galaxy formation and evolution, and that they suffer a dramatic evolution over the entire lifespan of the universe. Still, there are many, many questions to remain open. So, for example, try to understand this galaxy, or what are the progenitors of the massive and compact galaxies, what are the mechanisms that switch off the star formation? Is it really the supermassive black hole? And whether this mechanism is able to account also for the size and morphological change. So thank you very much for your time.
Thank you, Fernando. Is there any question? Okay. So then I will continue.
Perfect. Thank you.
Let me change to myself. And so hope you can see it. So my talk is going to be about the formation of the stars, and in particular about the accretion and ejection. Yeah. See, my laptop is a little bit slow. Okay. So, in this talk, I'm going to explain to you that not all the stars form in the same way, and indeed, the mass of a star determines how it's born and also how it's going to die. And although we have a very good overall picture of the entire evolution of a star, there are still many open questions, especially about how stars are born. So today I'm going to talk to you and explain to you how low mass stars form. That is how stars like our sun, that you can see it here, are forming. So as we will see, this is a very short phase of the entire evolution. Indeed, they spend most of their life in the so-called main sequence. That means that they are burning hydrogen. And for instance, our sun has already 5 billion years, and it is almost in its middle age, so it has still another at least 5 billion years to burn hydrogen, but its formation just took around 10 to 7, 10 to 8 years, so it's a very fast phase. Here I'm showing you where stars are born. So stars form inside molecular clouds, inside molecular clouds, sorry. So in the upper panel here in my slide, what I'm showing you is most of the molecular clouds in our galaxy. And here in the bottom right, there is a nice picture of one famous molecular cloud or star-forming region that is located in Orion. And all these tiny blue points are stars that are forming, but you can also see this appearance of these molecular clouds. That they really look like clouds, so they are forming. They are formerly of gas and dust. You can see the dust here represented in red. So molecular clouds are mostly composed of molecular hydrogen, and how the star formation starts, where it starts when a core within these molecular clouds starts to collapse. When it starts to collapse, it will form what we call a prestellar core in the middle of the cloud. And since the molecular clouds are rotating, the material cannot follow radially into the prestellar core, but it could form a circumstellar disk. And in this way, the material from the envelope that is composed of dust and gas will follow first into this circumstellar disk, and from there it will follow into the protostar. So, and as the time will pass, this envelope will be less and less massive, and also the circumstellar disk will pass from a very dense and circumstellar disk to a thin one, and at the end we will just have a debris disk, while planets will be eventually forming. But together with this circumstellar disk, what we observe is that in the early evolutionary phases, when the circumstellar disk is also very dense, we can observe protostellar jets. That is material that is being ejected from the system. And here on the right we have a picture This is an image taken with the Hubble Space Telescope of HH30. And here you can clearly see the protostellar jet that is emerging from the system perpendicular to it. And here you can see, or better not see, the disk because it's obscuring the light from the central source. And the protostar will be here, located in the middle. This is not the only example, and within the last 20 years, we have observed many circumstellar disks. You can see here. These are all Hubble space images of disks, and also protostellar jets. Indeed, the younger is the source, the more powerful are these jets. So this indicates that accretion and ejection of material is actually very actually connected, because when we do not have disk, and that means we are not accreting matter, we cannot observe these protostellar jets. And also tells us that this is a very good observational test of our current models, and that we are not so far from the truth. How this accretion and ejection take place? Well, we are not sure about that, but if we take a closer look into the star plus disk system, what we think we have is something similar to this picture that I'm showing you. So, as the matter is falling from the envelope into the disk, then this matter is traveling onward the system towards the protostar. The protostar has a magnetic field, and that will truncate the disk at a certain distance. And while the matter is traveling inwards, it will follow onto the protostar, following what we call accretion columns. Now, since the molecular cloud is rotating, also the disk is rotating because of the conservation of angular momentum. And if we will just accrete matter that is rotating onto the protostar, then this protostar will have to spin up and spin up until it breaks. So this does not happen because we actually have stars. So what we think is happening is that the protostellar jet is playing an important role, removing the excess angular momentum from the star disk system, slowing the matter in the disk, and then allowing it to accrete onto the protostar. But this is just an overall picture, and we have still many questions to answer. Indeed, the picture that I showed you before is just a representation, but we are not sure if the things are happening like that. So actually, we do not know how the matter is ejected. We do not know where it's ejected, from the disk, from the star, where it's happening. We do not know if this accretion and ejection processes changes with the evolutionary stage of the protostar. We have evidences that are like this, but we are not sure. Also, we do not know if these properties and the mechanisms for the accretion and ejection change with the stellar mass, or with the mass of the object. And we even do not know how high-mass stars and black dwarfs form. Do they form like low-mass stars? There are some evidences, but also we have contrasting theories. And we do not know how actually planets form within the disk. We have an overall idea of all these questions, but we do not know the details. And why is this happening? Well, this all is happening because of the small angular scales that are involved. So if you want to understand actually how the accretion happens and also how the ejection happens, you have to take a look to a very inner region within the star disk system. And actually, the region that you will have to observe is a region of the size, more or less, of the distance from the Sun to Mars. So this is a very tiny region. And as Eduardo explains to you at the beginning, if you want to resolve this region, so if you want to observe the details, you need a very big telescope, because at the distance where the nearest stars are forming, you will need a telescope of around 100 meters in order to observe this, because your angular resolution depends on both. the distance at which your object is. So the more distance is your object, the less spatial resolution you will have. And also, you need a very big telescope, because the bigger is the diameter of your telescope, the higher is your angular resolution. And so far, we do not have 100-meter telescopes. Our biggest telescope is a 10-meter telescope. You can find one in the Canary Islands and also in Hawaii. So how do we overcome this problem? I told you, as Eduardo told you before, we use a technique called interferometry. And that means that instead of being limited by the diameter of your telescope or your single telescope, what you use is the largest distances between the telescope you are using. And that determines your resolution. And here I'm showing you one of the optical infrared interferometers. It's the very large telescope interferometer. It's located in Chile, in Paranal, and it's one of the few interferometers that works at near-infrared wavelengths. We need to use near-infrared wavelengths because the innermost region of the disk emits at infrared emission. So we need to detect this type of light. And this interferometer technique is very new for optical and infrared astronomy, although it has been largely used for radio astronomy. And the biggest baseline, so the biggest distance that we can achieve with this telescope is 300 meters for the small units, and down to 150 meters for the 8-meter telescopes. We need 8-meter telescopes because in order to observe fainter sources, you need a big diameter. And using this technique, we have been able to detect the first circumstellar disk around a massive giant stellar object, so a massive protostar. And here on the bottom on the right, you can see the circumstellar disk around the source. It's not so spectacular as the image I was showing you before with Hubble, but this is a circumstellar disk. And we also know that perpendicular to the disk, there is a protostellar jet or an outflow for these massive protostars. And this result is very important, because it is a very strong evidence that massive protostars have disks and outflows, and then it forms like low-mass protostars. Indeed, there are two contrasting theories, one that assumes that high-mass protostars forms like the low-mass counterparts, and another one assumes that high-mass stars form from the merging of two or more objects. And the fact that here we have detected a circumstellar disk, at least for this object, is a strong evidence that massive protostars form like low-mass stars. And another thing that we are trying to do now is to study, to investigate the origin of accretion tracers. What are these accretion and ejection tracers? Well, the spectrum that we have from protostars is very rich in emission lines, like the ones we can see here, and we have understood that some of these lines, like for instance the forbidden emission lines and molecular hydrogen lines, are tracing the outflowing material, while lines like for instance the Bragg gamma line and hydrogen line are tracing the accretion. We think that because we have empirical relationships that relate the luminosity, the flux of this line with the amount of matter that is accreting onto the protostar. But our first interferometric studies of giant stellar objects show that in most of these objects, this Bragg gamma line is not tracing matter that is accreting onto the star, but is tracing outflowing material, and this was not expected at all. Now, on larger samples, they are not statistical samples because we do not have enough stars observed yet, But we're finding a trend in which lower masses stars, that in lower masses stars, the bracket gamma is tracing accretion, or at least it's being dominated by accretion, while in higher masses, this bracket gamma line is mostly tracing outflowing material. So this could indicate that there are differences in the disk or the near circumstellar structure when you change from lower mass stars to higher masses stars, high mass stars. And also this could mean that there is different physical conditions in the accretion and ejection region. So here are my conclusions. So I showed you that stars form inside molecular clouds, that protostars have circumstellar disks and also protostellar jets when they are formed, and that we have many unresolved issues like how does accretion and ejection proceed, is there any mass dependence on these processes, and some of these issues can be addressed through interferometric observations. So thank you very much. And if you have questions. Questions? Okay. No questions, so I will leave you just with, with a list for our next seminars, in case you want to reserve a day for this. And thank you very much for attending.